Hello, hello. So today we're going to continue... What the So today we're going to continue learning about generating functions. There's a cool little couple of facts that I learned recently about the two really neat generating functions I did in the last video for the Fibonacci numbers and the harmonic numbers. I'd also like to show what I got for Christmas. That's mathy related. You know, the rest of it is a couple records and all that. When I went to Barbados, I was reading Matt Parker's book on the way home, Things to Make and Do in the Fourth Dimension, on the plane ride back, and now I have Humble Pie, and it's fantastic. I absolutely love this book. It's all about mistakes in mathematics that affect like our everyday lives, and it's very, very interesting. I also got, if we're just going straight, for pure math nerdiness, I got G.H. Hardy's and E.M. Wright's book, An Introduction to the Theory of Numbers. So I get to learn a lot about the deep ins and outs of number theory, and I feel like there's probably a lot of cool stuff in here that I could show on this channel when I finally get to it. And speaking of things that I have yet to finally get to, I'm currently still reading Dr. Euler's fabulous formula, all about, e to the ix and all that, and I just read the chapter. It just is one proof that pi squared is irrational, which implies that pi is irrational. And I would love to share that proof with everyone at some point. So after I'm done going through the generating functions, I'm going to post that, and then we'll see where I go from there. Okay, so let's get into more generations. Okay, so sorry for that horrendous squeak. So let's recall what the generating function for the Fibonacci numbers was, right? It's the sum from k equals 1 to infinity of the we'll use n. So from n equals 1 to infinity of the nth Fibonacci number times x to the n. Start at 1, we get x plus x squared plus 2x cubed plus 3x to the fourth, etc., right? Where the coefficients are all just the Fibonacci numbers, starting at 1, 1, 2, 3, 5, etc. There's a couple things that I forgot to mention. So what we were able to show is that this is equal to x divided by 1 minus x squared. That function is, if we called this, what was it, f of x, right? Capital F of x, that's what we called it. And I realized I didn't mention the radius of convergence. So like the interval on the real number line over which this Taylor series converges, or whatever the radius is in the complex plane. It's some analytic function, yada, yada, yada. Really easy to figure out what that radius of convergence is, because look at the denominator. So what we're going to do real quick is we're going to apply something that we all know and love, the quadratic formula, to the denominator. So we're simply going to rewrite the denominator. So this is equal to negative x squared minus x plus 1. And if we do the Pythagorean theorem, we get that x is equal to, I'm sorry, not the Pythagorean theorem, the quadratic formula. X is equal to 1 plus or minus the square root of 1 minus 4 times negative 1 times 1, so plus 4, divided by 2 times negative 1, which is negative 2. Right? So that tells us that this is equal to, well, we can do a little bit of a simplification, so that's the simplification we're going to make there. And we can plug this in and factorize the denominator, right? So x is in the numerator, and then we have x plus 1 plus or minus the square root of 5 over 2. Put the minus out front there. So x minus 1, x minus negative 1 plus square root of 5 over 2, and x minus negative 1 minus square root of 5 over 2. Well, this negative distributes, and we get plus 1 minus the square root of 5, and this negative distributes, and we get plus 1 plus the square root of 5, which means negative phi, because that's the golden ratio, by the way, which is what you get when you divide one term in the Fibonacci sequence by the one before it, and you go higher and higher in the sequence, and that converges to exactly this number, 1 plus the square root of 5 over 2. As it turns out, 1 minus square root of 5 over 2 is actually the negative reciprocal of that thing. So that means that the negative of that, so 1 over phi, is the solution to that right there. Which means we can rewrite this function, capital F of x, as x plus 1 over phi times x plus phi, right? So the zeros are, sorry, that should be minus 1 over phi, sorry. So the zeros are 1 over phi and minus phi. The thing about that is that because this is going to be centered at the origin, there was no shifting, right? It's because I can plug in 0 and all of it's 0, so that is sort of the idea. That means that the radius of convergence, the absolute value of x, has to be less than 1 over phi, right? Because once this is like way out of the thing, you could do like, what's the word? You could do a contour integral around this 0 instead and get like a different but equal analytic function, right? Taylor series expansion, right? I think that's how that works, right? But on just the real number line, since we're centered at 0, this is as far as it goes, right? 1 over phi units away from the origin. So that's the radius of convergence of that function, but I wanted to take a look at one more thing to do with it, because if we take a look at the original definition that we had, which is this right here, 1 minus x squared, we can actually generate a bunch of series that approach really nice rational numbers using the Fibonacci numbers. So all we have to do is, if we're counting in base 10 like we humans normally do, so what we're going to do is we're going to let x equal 10 to the minus k plus 1. That means that this is equal to 10 to the minus k plus 1 up top, divided by 1 minus 10 to the minus k plus 1, minus 10 to the minus 2 times k plus 1. So we're going to multiply by 10 to the 2k plus 1 on the top and bottom, and we're just going to multiply those in. And we end up with 10 to the k plus 1 in the numerator, divided by 10 to the 2k plus 1, 2 times k plus 1, sorry, minus 10 to the k plus 1, minus 1. But now look at what we have. We have something that's just a nice, neat, rational number. So say we pick k to be, well, actually what we should do is we should also replace it in our original definition, right? We're replacing x with 10 to the minus k plus 1. So what we end up with is f, the nth Fibonacci number, divided by 10 to the minus n times k plus 1, right? That's kind of easy to follow. So we end up with these cool series where we have Fibonacci numbers being divided by larger and larger powers of 10 that add together to make really, really nice numbers. For example, let's pick k to be equal to 0. So if we pick k to be 0, we're just going to make room here, and we're going to say let k equal 0. So then we have what? We have the sum from n equals 1 to infinity of the nth Fibonacci number divided by 10 to the negative n, right? So we're simply just raising, whoops, I apologize. Many of you may have noticed that negative should not have been there, right? Because I moved the 10 to the denominator, the power of 10 to the denominator, so it shouldn't be negative anymore. So I changed the sign of that. So it is just 10 to the n in the denominator if we take k to be 0. And so what we get is the first Fibonacci number divided by 10, the second Fibonacci number divided by 100, etc., etc. And it's very, very nice because look what we get. We end up with 10 to the first power, so 10, divided by 100 minus 10 minus 1. So we end up with, what do we get? We get this sum over the nth Fibonacci numbers divided by the nth powers of 10. We get 10 divided by 89. Which is kind of a shocking result, right? It doesn't seem like it should be the case, but somehow these things are related. And if I'm not mistaken, I believe 89 is a Fibonacci number, right? Because 34 plus 55 is 89, right? So yeah, 89 is a Fibonacci number, just coincidentally. I'm pretty sure that's probably related. If you were counting in a different base for some reason, then you would just pick a different power, right? We could do the Fibonacci numbers over powers of 2. Let's just quickly see what that looks like. So we're going to do powers of 2 instead, and what are we going to end up with? We're going to get, well, hang on, let's change this. So we're going to plug in powers of 2 instead. Just change all the 10s to 2s. It's not very hard, right, in all the steps, and we'll end up with this. 2 to the k plus 1 divided by 2 to the 2 times k plus 1 minus 2 to the k plus 1 minus 1. So if we just plug in any k equals 0, again, we get the Fibonacci numbers divided by powers of 2, and that gives 2 divided by, and what do we get? We plug in 0, we get 4 minus 2 minus 1. So we get, 4 minus 2 minus 1. That's 1. We get 2. Look at that. That's really interesting. I never even thought that would happen. That's really funny. You actually just get 2 if you sum up the Fibonacci numbers divided by the powers of 2. So, because we'll get 2 squared minus 2, which is 2, minus 1, which is 1. So that's very neat. I didn't know that going into this. So that's all the facts I'll show you about the Fibonacci one that we just discovered. And then I want to sort of do something about the harmonic series that we discovered. So what did we have? We had that capital H of x, which we said was equal to the sum from k equals 0 to infinity of the kth harmonic number times x to the k. Right, and we discovered that this was equal to minus the natural logarithm of 1 minus x divided by 1 minus x. And I showed that you could write this in a funny way, right? Like this, right? Where I brought the negative 1 in as a power and then brought the denominator out as a product. What I realized was we can rewrite 1 over x as e to the natural logarithm of 1 over x. So we have that this is equal to the natural logarithm of 1 over 1 minus x times e to that same thing, the natural logarithm of 1 over 1 minus x, because this is just that, right? They're inverses of one another. And so now we can use the Lambert W function, which if you recall, if we have y equals t times e to the t, then by the definition of what the Lambert W function is, we have that w of y, the inverse function, is equal to t. So this thing undoes this function here, right? Something times e to that same thing. And that's exactly what we have right here. We have this times e to that same thing. So if we take the Lambert W function of both sides, so w of h of x, where this is h of x, we end up with just the natural logarithm of 1 over 1 minus x. Raising e to both sides, we get that e, and we can do the reciprocal and take the negative back out, and we get e to the negative w of h of x is equal to 1 minus x. So we have this very strange identity that 1 is simply equal to x plus e to the minus w of h of x, where w is the inverse function of t times e to the t, and h of x is this generating function, this thing right here, of the harmonic series. Of the harmonic numbers, sorry. So these are all very, very interesting facts that I wanted to show you, and there's a couple other things that I actually wanted to do in this video. Quick little thing, this channel has an Instagram, so it is at what the hectagon, of course, and it has a Twitter also. So this is Instagram, and of course this is Twitter, and it is of course naturally, also what the hectagon, at what the hectagon. Nope, at the hectagon. Oh, can't spell today. Okay, hectagon. And my email is the incorrectly spelled what the hectagon. Why spell check before you make the email right, that you can't then change, at gmail.com. Now all of these are in the description if you don't want to have to somehow watch the video and pause it and actually write it down. Along with other Instagram, Twitter, YouTube accounts that me and my friend Bill run. He does one for D&D. We together stream on Mixer under the moniker of Fredwood Live. So check the description for other stuff. This is just for my channel. This is my Instagram, at whatthehectagon, Twitter, at whatthehectagon, and email, at whatthehectagon, because I spelled it wrong when I made the email and now I can't change it. So that's the stuff. Thank you for watching, and bye-bye.